For a circular motion lab, we looked at the relationship between the velocity an object has while moving in a circular path at a constant speed and the size of the sum of the forces needed to keep that object moving in that same circular path. In our pre-lab discussion, we noted that the sum of the forces on the object moving in a circular path needed to always be pointed towards the center of that circular path. We collected for a given mass object at a constant radius the size of the sum of the forces on the object and the velocity of that object for different trials. We then graphed the sum of the forces on the y-axis and the velocity on the x-axis, and here's two examples of whiteboards from student data. In one example, when a group graphed as the velocity changed, the sum of the forces increased in a parabolic fashion, and so they re-expressed that graph as a linear relationship by squaring their x variable, or in this case, squaring velocity. They found that when they graphed the sum of the forces versus velocity squared, they got a straight line, and the algebraic representation was the sum of the forces is equal to the slope, which is 0.03038, times velocity squared. Below you can see these were the initial units of the slope. It was newtons divided by meters squared over seconds squared. Expanding the unit of a newton into a kilogram times a meter per second, they showed that everything cancels and simplifies to just give us a unit of kilograms divided by meters. So this was 0.03038 kilograms per meter. We'll discuss in just a little bit what that ended up representing. A second example of data showed that also, again, when this group graphed the sum of the forces on the object that was pointed towards the center versus different velocities when the object was moving in a circular path at a constant radius, it was an exponential relationship. They also re-expressed that graph as a straight line by squaring the x variable, and so they also got the equation to predict the size of the sum of the forces needed to keep their rubber stopper moving in a circle, in this case at a constant radius of 0.17 meters, was equal to 0.0755 newtons divided by meters per second squared, all times their velocity squared. So this group got a higher slope value. So using the second whiteboard and the second data set, we can see that the equation where the student group is able to predict the size of the sum of the forces to keep their rubber stopper moving around in a circular path is just multiplying 0.0755 times whatever the speed is of the stopper squared. When we look at the simplified units of the slope, we get kilograms per meter. That suggests that the slope might be some kind of ratio that stayed constant, maybe a mass ratio divided by some distance ratio because it's kilograms divided by meters. So when looking at this ratio, several groups realized that they had a mass that stayed constant. That was the mass of the stopper, and there was also a distance that stayed constant throughout the experiment. That was the radius of curvature of that stopper. For this particular group, the mass of the rubber stopper was 15.5 grams, or 0.0155 kilograms, and the radius of curvature that they chose to use was 0.17 meters. So if we look at their ratio of the mass of the stopper divided by the radius of curvature, you get 0.0155 kilograms divided by 0.17 meters, and that gives a value of 0.091 kilograms per meter, which is awfully close to the value of the slope that they got on their re-expressed linearized graph. A number of groups in both classes got the same thing. When they took their constant mass divided by their constant radius, that value in unit was very, very close to the value of their slope. We looked at that and then generalized the results. That the slope must be the ratio of the mass to the curvature, the radius of curvature of the object moving in a circular path. If we group the two variables in the numerator, mass and velocity squared, we get that the general relationship to predict the size of the sum of the forces pointed towards the center of a circular path needed is equal to the mass of the object moving in the circular path multiplied by its velocity squared, all divided by the radius of curvature. Now, if you're in AP Physics 1, this equation is not on your AP Physics equation worksheet. We know that Newton's second law allows us to substitute for the sum of the forces, the mass times the acceleration of the object. So we're going to write the mass of the object times its acceleration is equal to mv squared over r. And we can see that the mass variable cancels. And we get that the acceleration of the object that's moving a circular path is equal to its velocity squared divided by the radius of curvature. And this is how it looks on your AP equation sheet, that the centripetal acceleration is equal to velocity squared divided by the radius of curvature. And for our formal lab report, in the conclusion, our new term will be the centripetal acceleration. Now remember, this stopper was moving around our circular path at a constant velocity, approximately a constant velocity. I take that back. The stopper was moving around the circular path at a constant speed, but not at a constant velocity. Remember, velocity is both speed and direction, so even if the speed is staying the same, the direction is constantly changing, so we'd still say that the stopper was accelerating. Well, remember, the acceleration of an object will always be in the direction of the sum of the forces on that object. And in this case, the sum of the forces was always pointed towards the center, and so the acceleration is always pointed towards the center. So the centripetal acceleration is the inward pointing acceleration of an object moving in a circular path.